All right, so what the logarithm actually is it says 10, here we got our 100 billion factorial.
Yep.
Here.
Yeah.
It says 10 to this power is equal to 100 billion factorial, okay? So normally we would say 100 billion factorial is just some number, and now we're trying to figure out the power of 10 that makes 100 billion factorial. But we can ask the same question about, like, for example, what power of 2 would make 100 billion factorial?
So we could do base
Log
2.
base 2. And that's a gigantic number. In fact,
Actually, that's close.
funny enough.
That's close to 3 to the 3 to the 3 to the 3.
Right. So, but it's not the number of digits anymore. Although it would be the number of digits in base 2,
Yeah.
which is kind of fun. So if you wrote 100 billion factorial in binary, it has about the same number of digits as 3 to the 3 to the 3 to the 3 does in base 10.
What?
There's a funny coincidence, right? And it turns out, believe it or not, that there's actually a very special logarithm number that most mathematicians use. And in fact, they call it the natural logarithm. And we'll see if this is what Wolfram Alpha defaults to. I don't know, but we can check by looking at log of 3. Bigger than 1. Okay, so we know this isn't defaulting to
It
log.
actually says assuming log is the natural logarithm.
Oh, okay, there you go. So it defaults to that, and it nicely tells you that it defaults to that. But we would have known already that this wasn't base 10 because 10 to the 1 is bigger than 3.
Yeah.
Right? And we round up for the number of digits when it's base 10, and we know 3 does not have 2 digits.
No.
Okay, so the interesting question is, what number is this natural logarithm? We know it's a little bit less than 3 because you have to raise it to a power bigger than 1 to get to 3.
Well, that kicks out pi.
So it's right, it's not pi. Let's check 2. Oh, it's less than 1, 0.6931.
So if we round
So it's
it up-
between 2 and 3, whatever the base is for this logarithm. Maybe check 2.5. Check in the middle.
It's about 0.9.
So the base has to be bigger than 2.5.
How
So
about
we could try-
2.75?
2.75, we'll just keep splitting the difference.
We get
Oh, a little bit
something
bigger.
bigger. So it's between 2.5 and 2.75.
So how about 2.62? Or
Do you want to go in the middle? How about this? 2.71828. 18.
that's E.
Huh. Huh. E. E shows up, so I almost get 1, right?
Yeah. But you have to go in for infinite to get 1.
What if I just put an E?
Log E.
Log of E.
1.
Hey!
Huh.
Log.
So E turns out to be a very special number.
So you have to use the log function in base E to get
So
1.
mathematicians and physicists, and really a lot of other people too, use base E a lot. That seems strange, right? Because
Yeah.
you don't feel like you encounter base E very often.
No.
Yeah.
And I don't mean base as in a number system like counting in base 2 is binary. I mean the base for the logarithm. So E becomes a very natural number in math and in physics.
Cool.
And I'm going to show you some areas where it comes up in math in the next video. Okay.
Okay.